All right, well, expect a few more to probably filter in, but we'll go ahead and start the seminar series. Today, it's my pleasure to introduce Roy Sando, and Roy is a supervisory research physical scientist at the Wyoming-Montana Water Science Center and is physically based in Helena, Montana today. Research focus is on geospatial modeling and statistics, machine learning and remote sensing of hydrology and water budget components. So without further ado, I'll go ahead and turn the podium over to Roy and take it away whenever you're ready.
Awesome. Thanks, Tim. And I trust that somebody will tell me if you can't hear me or see me, so please do. So yeah, today I'm going to talk about a handful of projects that we've been working on over here at the USGS, intermixed with colleagues from other agencies as well, including your very own Kendra Kaiser, who started out doing some of this work for us over in the Boise River Basin. A lot of it has to do with machine learning and some techniques that we've adapted to advance these methods to larger regional scales. Some of it doesn't have to do with machine learning, so the title is a little bit of a misnomer, but either way, it captures a lot of what we've done. I also want to acknowledge a handful of folks on here, also from the USGS, including Chris Yeager, who's on the call today in the audience. Also colleagues from Oregon, Idaho, Oklahoma, Texas, and in Corvallis, Oregon at the Forest and Rangeland Ecosystem Science Center. Okay, so perennial, non-perennial classification. I'll be referring to this as streamflow permanence, probably using it interchangeably, intentionally or unintentionally throughout the talk, but they both mean the same thing. Non-perennial streams are extremely important. This has been studied pretty extensively across CONUS and across the globe. And it turns out they make up almost 80% of the total stream network. However, despite their prevalence, mapping of non-perennial headwater streams is still inaccurate. A lot of this is largely due to observational bias. Imagine you're walking through the mountains or wherever you like to go, prairies. It's almost always easier to identify and study water when it's there, right? It's a lot harder to be intentional about walking across a channel when it's dry and saying, okay, what's the water doing in this when it is flowing? So because of this and other reasons, the mapping of our non-perennial headwater streams is still inaccurate. Despite that, there's a lot of regulatory implications for perennial versus non-perennial streams. If you look at the Clean Water Act, for example, there's a lot of differences in what you can do and can't do in non-perennial systems versus perennial systems. For example, if you want to harvest timber in a non-perennial drainage, there are much fewer restrictions there. Whereas if you're working on a perennial stream, you have to be at least 100 meters away from the stream before you can harvest that timber. There's also regulatory implications associated with annual grazing permits, so where you can and can't have cattle or bison or other livestock. And also water withdrawals. Obviously, where there's more water, you can withdraw more water. But when that water isn't running, there's more limitations on the permitting, and also there's calls. More often, there's calls there when that water shuts off. Again, despite all of this, there's really very little we know, or not very little, but our mapping remains inaccurate. And as we've shown, this is incredibly important because of these reasons. So springboarding off of that, with our streamflow permanence work, particularly here in the USGS and across others, there's a lot of experts even on this call. A lot of what we've been trying to do with our projects is answer the objective or meet the objective of getting to year-round flow, predicting year-round flow that improves on spatial and temporal accuracy of existing models. So we have examples, numerous examples of areas that flow one year and don't flow another year. And typically those are captured in static predictions, but we want to get to the point where we can model and predict those locations and the flow in those locations on an annual basis, and even up to a daily basis. And I'll talk about that effort here in a little bit. So again, just a visual example of what we're trying to move towards. The National Hydrography Data Set with USGS is the most widely known and used hydrography data set in CONUS. And again, their streamflow permanence classifications are static. So regardless of the amount of flow in a system or the amount of flow in a year, they're going to have the same flow classification for all systems across all years, and they're static. However, what we want to get to, and what we have been publishing and improving on, are dynamic predictions. So as you move up and down the stream, we want to capture those climatic conditions of that year and the climatic conditions of each location as best we can. So I'll talk briefly a little bit about the background of this, and this is just the background that I've been involved in the USGS. There's other studies I want to acknowledge, but obviously I don't know about them to the extent that I can present on them, so I'm going to present on my work. For me, this all started in the Lower Clark Fork in Northwest Montana. The foundation of this was that the Forest Service had some bull trout remediation, habitat remediation they were doing up there. In one year, I believe it was 2012, we had a pretty dry year up there. And they went up to some of their sites and realized that there was no more water in the system, which is not necessarily anything new to folks, but it occurred to them that we should probably study this and get a handle on where these streams are predicted to be permanent versus where they have a higher tendency to dry up in a given year. So we launched a study in the Lower Clark Fork to come up with a predictive map of where these streams dry up in a given year. The thing about this study was it was catchment scale. We limited it to first order streams to reduce the complexity. We only included about 5 covariates, and we modeled typical conditions. So it was an average over these years. Some things that popped out were local geology. So surficial geology was really important, with alluvial deposits or glacial lake deposits being more associated with subsurface flow. And another thing that popped out was snowpack persistence. So the amount of snow-covered extent normalized by winter precipitation had a significant impact on whether or not these systems flow year-round. And what that means is, so if you get the same amount of snowfall in one catchment versus the other catchment, the catchment that retains that snowpack longer, we quantified the effect of that on essentially the probability of that stream retaining stream flow year-round. What this produced is this left figure here. Again, essentially the probability of stream flow permanence. And you can see that, yeah, it follows what you'd expect generally. The accuracy on this was about 80%, which you'll hear me reference over and over because that seems to be kind of the ballpark accuracy for all of our models. But again, this laid the foundation for our flow permanence modeling moving forward. A thing to note is that this wasn't just taking place in the Western US. At a similar time, our colleagues Gardner Bent and Pete Steves over in Massachusetts had developed a logistic regression equation for estimating probability of, actually not probability, classification of perennial and non-perennial streams in the Shawsheen River Basin in Massachusetts. So not just a Western US problem, again, a CONUS problem. So expanding on this, the next step was to take what we did in the Lower Clark Fork and expand it to the Pacific Northwest. Obviously, this is a phenomenon that occurs beyond just the Lower Clark Fork, and a lot of agencies and groups wanted to get a handle on this, where streams are dry and where streams are flowing in a given year. So we expanded this effort, and this became what we call our probability of stream flow permanence project, or the PROSPER project. A big challenge here, though, is what data we were going to use. So historically, USGS is known for a stream gauging program, which is great and provides a lot of great data. However, it's been recognized widely in CONUS that there's a bias associated with those stream gauges. They're typically on larger perennial systems that have high recreational value or high water consumptive value. And once you get into the headwaters, the representation of headwaters and subsequently intermittent streams falls off. So what we were trying to do here is we mined multiple data sets and worked with 11 different federal, state, tribal, and local agencies to come up with about 24,000 observations. We processed those into a little less than 4,000 wet or dry observations to use for model development. And the reason we had to cut that down so much is because we had to pair it with our input predictor variables. We had to balance it for the machine learning models, et cetera, et cetera. So even though we started out with quite a large number, it got cut down to about 4,000, which is what you see here. So this was our final input model, or input training data, sorry, across Pacific Northwest. And you'll see in Idaho, actually, we had tremendous participation from particularly state agencies, Idaho DEQ, others, Boise River, University of Idaho, and others in Idaho to get a pretty good density of observations in Idaho. So you guys were well represented in our training data. As for the modeling approach, so that covered the training data or the calibration data, the response variable, but we also needed to get to our predictor variables, our explanatory variables. And what we decided to do here was incorporate what we call a flow condition parameter grid explanatory variables. And so what these represent is essentially as you move down the system, each pixel will represent the upstream conditions for every basin in your network. So we created these 30-meter grids for the entire Pacific Northwest, which represented topography, land use, soils, permeability, and a base flow index. And then we also incorporated dynamic variables, including precipitation, temperature, snow water equivalent, and evapotranspiration. So we combined all those into a random forest predictive model, which allowed us to predict annual stream flow permanence at every pixel in the Pacific Northwest from 2004 to 2016. And again, that 2004 to 2016 really was limited by the period of record of our explanatory variables. And what we found was in the Pacific Northwest, the things that popped out, precipitation was most important, variable. Temperature coming in second, forest cover, and base flow were the top four. One thing to note here, though, is that we didn't include drainage area. And this was, we went back and forth on this a lot. It was kind of a head scratcher to most hydrologists, I think rightfully so. But the reason we didn't include it was the argument that drainage area is particularly not a causative variable, but more likely an associative or corollary variable. And so we were hoping that we could explain that the variance through things like precipitation, land cover, etc. We have started to include that because it was probably a little bit naive that we excluded that in our first go around. But so if we take the results from our first Prosper model and zoom into the Boise River Basin, you can really start to see what we're hoping to depict as these dynamic systems, not necessarily static. A stream is either flowing or not flowing, and that's the way it always is. But really, people should start thinking about these as dynamic zones that expand and contract based on how much water enters the basin. So if you look here, this is 2008, and you can see the blue lines represent streams that have a greater than 0.6 probability of year-round flow, and the red represent streams that have a less than 40% or 0.4 probability of year-round flow. And if you look at 2015, which is a particularly dry year, you can see how the perennial flow lines contract and the non-perennial flow lines expand in the basin. One thing to note is what we're predicting here is just annual conditions. So there's no information on timing, duration, or the frequency of no flow conditions within a given year. We are working on models that will provide daily predictions, but I'll talk about those in just a little bit. One cool thing that this allows us to do is look at the prevalence or the occurrence of these conditions. So here, what we're looking at is over that 14-year period of record, what locations are predicted to be intermittent the entire time versus only a few years. And conversely, here we're seeing predictions that are predicted to be, or locations that are predicted to be perennial up to 14 years, and you can see the degree of perenniality indicated by the shade of blue here. So once we completed our Pacific Northwest modeling effort, we moved over to the Upper Missouri River Basin and made a handful of changes and improvements to the modeling approach. So one big thing that we did was we stratified the input. So with machine learning, it's a machine learning classification. It's important to have balanced data as your input. Otherwise, it kind of throws off the modeling confidence. So what we did was we balanced by ecoregion and bootstrapped that. So we created multiple models and then took an average of that at the end, which allowed us to represent each ecoregion in a balanced manner. We also included drainage area as a covariant and produced our model uncertainty as a result of spatial cross-validation as opposed to random cross-validation. Another thing that we included was our geographic patterns and variable importance. So what we could do is we could look at each site and say what is the most important variable for that site. And if you do that across all the sites that you were used in the training data, you can come up with these patterns and hopefully understand what variables are important in your region of the study area. So again, these are all available. All these results are available in the Sando et al. Journal of Hydrology X publication. But one covariant I would like to highlight in this is, so when you're out in these arid prairie lands, one thing that you can do is you can look out and see typically where the permanent water is based on the type of vegetation on the landscape. And it's really cool because you'll look out and you'll see this kind of this brown swaths with these really bright green, woody, permanent vegetation strips through them, which are usually indicative of either shallow groundwater or permanent surface water in the low flow season. So exploiting this fact, we developed a cloud-based approach to creating harmonic regression coefficients for each pixel, each 30-meter pixel in the study area, which allowed us to get the annual green up curve. So we incorporated those coefficients, which are displayed here in the bottom right-hand panel. We incorporated those in our modeling, which turned out to be about the fourth most important variable in this Upper Missouri modeling effort. And what it allowed us to do was really distinguish between water limited and energy limited vegetation. So in the upland areas, you have these prairie grasses that are water limited and don't have access to water throughout the year. In the riparian zones surrounding perennial streams and systems, you have vegetation that is more energy limited because it does have access to water year round. You can also see the agricultural fields, the irrigated agriculture, popping up as energy limited as well. So here's the results of our Upper Missouri modeling effort. And things to note here. So drainage area, I alluded to the fact that we started incorporating this in our modeling moving forward. Drainage area is the most important variable, followed by wetlands and developed area. And then finally temperature, that NDVI variable, and elevation. So a big thing to note here is differences in important variables in the Upper Missouri or Central Great Plains. It's shifted more to land cover and surface wetland area, as opposed to the Pacific Northwest that was more dynamic climatic variables like precipitation and temperature. So just some interesting things to note there and probably topics of future study as well. So going back, these were kind of our big base regional streamflow permanence models, but we wanted to start going back and taking a deeper dive into what drives these models, what's important and what matters. And we found four distinct things that popped out. So the scale of the analysis matters, your input data proximity and representation of your basins, prediction uncertainty is important, and then finally model extrapolation. And I'll go into this in a little bit more detail here. So what we found out here was, again, Chris Yeager, my colleague over in Washington, got a project funded to look at Mount Rainier. And if you look at this bottom left-hand figure, what this is showing is the standard error of prediction. And you can see these highlighted areas that have a little bit higher standard error of prediction, again, associated with a lower representation in the model. So Chris got a project funded to look at Mount Rainier. The north arrow on the lower left figure. And I just take a deeper dive into streamflow permanence in that area and what drives streamflow permanence. So what we found here is that local data collection makes a difference, right? So these data densities here in the bottom right histograms, despite the fact that our regional model had greater accuracy, so about 81% versus 74% in the Mount Rainier model, what we're seeing is the Mount Rainier model was able to better differentiate those permanent versus non-permanent locations. So again, in machine learning, you often hear like more data is always better. It's always better to include more data. And generally that's true for overall model performance. But what we're showing here is that it matters, the scale matters. And when you dig into these local conditions, despite the fact that your general model can have greater accuracy, the incorporation of better local representation drives better distinction in your classifications at the local scale. Another thing that colleagues at the Forest Service, Jonathan Burnett and Chris Yeager, USGS, looked at, so they got the projects funded in Western Oregon. And one of the things they wanted to look at was how much of a difference does it make to have data within a basin? How much of a difference does that make for the basins with data in terms of model accuracy? So what we call this is proximal versus distal data cross-validation. So we isolated those basins that had data included in them and looked at the cross-validation results for those basins versus the basins that did not have any data within them. And what they found was for basins with data located within the basin, the model accuracy was 83%. However, when you look at basins without any data, that model accuracy dropped down to 67%. So again, associated with scale here, where you have your data and what type of representation is associated with your data is important for model accuracy. And what they found is essentially model performance was best when using sites with greater than 10 visual observations. So this is essentially associated with the streamflow duration at a given location. The next thing that we wanted to do was include uncertainty in our model prediction. So revisiting our Prosper Pacific Northwest model output, we acknowledge that there's uncertainty in these predictions, right? However, in our first attempt or our first publication, we didn't include uncertainty in the outputs. So we went back and reran the models and looked at the ensemble of trees associated with each prediction and grabbed essentially the spread of those predictions for every site. And what you'd expect here is that around 0.5, predictions of 0.5, model uncertainty increases. And that's exactly what we saw. So you can see here in the plot A on the lower right-hand side, the uncertainty associated with both intermittent and perennial predictions, and they increase as you reach the other end of the spectrum, essentially. What this allows us to do now is our published predictions have uncertainty associated with them. So previously, if you had a prediction around, say, 0.54, we would have just called that perennial. But now we can call that perennial with high uncertainty or potentially non-perennial, depending on how you're looking at it. And now these uncertainties are also included in our published predictions. Finally, the extrapolation piece. So Jonathan at US Forest Service went back and created a vector machine model to predict which basins, how much of each basin was extrapolated outside the model. So again, another part of these published predictions is essentially how confident are we in these predictions based on how much of the stream network is extrapolated beyond what was used to train the model. And this is really important in machine learning and really even parametric modeling. Extrapolating beyond the range of your inputs is often a very fast way to lose credibility in your outputs. So what we're doing here is we're providing some information on which basins we're more confident in based on how much of that basin has extrapolated predictions. Okay, so that kind of wraps up where we're at to this point. Moving forward, I'm going to start talking about what's in the works and what our team is working on. So Nate Shelgren over at USGS Forest and Rangeland Ecosystem Science Center has been working on a Bayesian approach. And this is really leveraging the fact that we have all of this previous knowledge and previous data incorporated in things like our observational data sets. So the National Hydrography data set that I showed earlier, despite the fact that that's outdated and often collected back in the 1900s, there's still a lot of good information in those observations, right? So what Nate has been doing is using those observations and all the observations we have available, including our citizen science app, Floper and Roadster, our Prosper Northwest predictions, our stream gauging network. He takes all of those and then conditions the prior probabilities for his Bayesian model based on those observations. He also incorporates spatial autocorrelation. So essentially where we have data, he penalizes locations for being closer to other observations. And that way, essentially, you don't overload the model and overfit it to observations where you have data, but you allow the model to learn from those observations and say, okay, well, if a prediction is closer to an observation that says it's wet, more than likely, there's a higher likelihood that that prediction or that location at the ungauged location is more likely to be wet. So a couple big improvements here. Another thing is that he can make, with this Bayesian model, we can make predictions for daily conditions. So again, previous to this, what we've been doing is making predictions for annual conditions and really just calling a system either wet or dry. What we're getting at with this Bayesian approach is daily conditions. So it's a lot of data and it's difficult to run for large swaths. But if there are areas of interest or points of interest that somebody wants to know what the daily conditions are, we can run those predictions for those points. And here's two examples of that. So we have an example for a stream that goes dry periodically and a perennial stream that never goes dry from 2015 to 2025. And you can see how the Bayesian predictions actually capture these seasonal dynamics in the intermittent stream. And yet in the perennial stream, it's also able to capture the fact that it never really goes dry. So some very cool updates coming there. Another thing that this can be used for is a prioritization map for future sampling. So a big question people often have is, well, if we're going to go collect more data, where should we collect data? And oftentimes it's a complicated answer that we can't very well articulate. However, with this prioritization map, we can actually quantify how valuable these locations are in terms of model information. So it's associated with predictions close to 50% in our streamflow permanence models. And essentially what those translate to are prioritization scores of about 1 for the sampling map. Another important thing about the models we're working on now is that they're flexible, which means we'll be able to incorporate multiple hydrographies. And the hydrographic map that you're looking at here is showing essentially our high resolution national hydrography data set in the blue, the lower coarser resolution. And then on top of that, the pink are LiDAR based hydrography. So you can see how these change. We're thinking about that in terms of model development, and being able to incorporate this as they change will be important. So we do have visualization platforms available. So the Upper Missouri Prosper data output are available on our USGS Prospera map viewer. We also have a water, which is a provisional map viewer for the Western Oregon wet dry model. And I'd be happy to share those links upon request. Another platform that these predictions are available on is the StreamStats network. And this is relevant for Idaho in particular. So all the Pacific Northwest predictions are available on StreamStats. And what comes with that, when you get into StreamStats and look at the Prosper tool, what we allow you to investigate and visualize are nearby field observations. So you can see, if you look into, if you have a spot of or a location of interest, you can go in and actually see what observations or training data are available nearby. You can see the NHD streamflow classification here in panel F. So it'll show you what year the NHD classification was made. Typically, this record year is going to be sometime in the 1900s. And you can see the classification associated with that NHD reach. We also wanted to provide some climatic context for these the observations. So we'll provide the Palmer Drought Severity Index for the year of observation associated with NHD. And then we also provide our Prosper predictions for that location and show how those compare to the self-calibrating Palmer Drought Severity Index. So a lot of information included in the StreamStats platform. And again, that's all available to the public and currently published. So just some key points about what we've learned about modeling streamflow permanence. Typically, our model accuracy remains in the low 80%. Drainage area is a persistent, important variable, but it's important to note that this is likely correlation and not necessarily causation. Think about a larger bowl. If you're catching water in a bowl, a larger bowl is able to catch more water than a smaller bowl, and typically tends to produce perennial systems the larger you get. Also, crowdsourced data collection is effective, but there are trade-offs. We're finding that it's very difficult to publish these data and clean them up because oftentimes the GPS accuracy is questionable, or there's errors associated with them. So the publication and data release process is more onerous than we anticipated. Okay, so in the works and future products to be on the lookout for. So increased data collection, obviously we're using Floper and other apps to go out and collect data on the landscape. Developing models that have streamflow from physical models as predictor variables. So combining these machine learning with process-based modeling efforts to come up with more informed models. Improving extrapolation in areas of applicability. So understanding where we can apply our model outputs and how confident we can be in those predictions. Predicting based on model ensembles. So as we develop more modeling approaches and methods, not necessarily getting rid of the old ones, but coming up with an average or ensemble of those predictions will be most informative. And finally, incorporating off-channel surface water dynamics. So linking up our streamflow permanence models with observed surface water dynamics from remote sensing will allow us to come up with more holistic products. So quickly, talking about our crowdsourced data collection, Chris and others have published a citizen science app called Floper, and this allows for just a quick capture of wet and dry conditions. The team has been using this across Pacific Northwest. It's super easy. I do a lot of hunting in the fall, and so it's nice just to have that app on my phone as I'm out hiking through the woods. And as I walk across a channel or something like that, it's just literally like a 15 to 20 second exercise to grab those conditions. Currently, we have over 25,000 observations that we're cleaning up and in the process of publishing. So as I mentioned before, processing the flow for data can be a challenge. The accuracy of these observations is often limited by the power of the GPS that a person is using. And you can see here in our examples to the right that oftentimes there's a fair amount of work that has to be done to link these observations to the correct channel. However, we do have a workflow that we're working on to automate this procedure. So we're hoping that we'll capture the majority of the data accurately. There's always room for error in this stuff, but we've come up with a method that we think is sufficient for improving the accuracy of these snapping exercises. Next, predictions based on model ensembles. So again, this is just essentially taking multiple modeling approaches and combining them into a single ensemble and allowing the outputs to contain some information on uncertainty and an ensemble of those modeling outputs. Also, we've acknowledged the fact that as people collect more data, we need to leverage and incorporate that information in the modeling approach. So we're working on a smart modeling approach in the Pacific Northwest where every year we recalibrate our models and repredict based on newly harvested streamflow permanence data. So with the Floper app and other apps, those data that are collected every year, we can go out, harvest those observations, pull them into our modeling approaches and recalibrate our models. And this allows stakeholders and end users to also identify streams that we don't have much information, go out, collect new information and new data there, and allow our models to learn for those local systems. Finally, incorporating off-channel water extent. We have a project that is, our publication is currently in review. But essentially, the idea here was to combine our Prosper modeling output for streams with the dynamic surface water extent data set for off-channel water bodies. And what this looks like is, so I just have an example here for a wet and dry year. 1996 was fairly wet, 2006 was dry. There's two different products that you're looking at here. In the stream channel, this is our probability of streamflow permanence predictions. In the reservoir, it's the DSWE product. So you can see during the wet year, the reservoir expands, the permanent stream channel expands. However, when you get to a dry year in 2006, you can see the reservoir contracts quite a bit, and we lose that prediction of perenniality in the stream flowing out of that reservoir. So when you combine those over the period of record, you can get a handle on how often these locations are inundated. And what that allows us to do is come up with an index over time of anomalies. And a cool thing that we've looked at here is how streams respond to climatic conditions versus wetlands in the same area. And we have three examples on the lower left. One example shows where you see a correlated response. So when streams expand, you also see an aerial expansion of those wetlands and surface water bodies, indicating that there's some dependent response there. Another basin shows us essentially independent responses. So it really doesn't matter what streams are doing in terms of how the wetlands are responding. And finally, up in the prairie potholes region of the Upper Missouri River Basin, you see here a negative correlation between wetlands and streams. So when streams expand, wetlands contract, and vice versa. Again, this publication is a review, so all this is very new and off the press, and we're excited to look into it a little bit more. You can also compare, so the SWIPE index is the first look at empirical observation on the landscape in terms of a drought index. So we wanted to compare this to an atmospheric drought index, the SPEI. And so you can see how the land surface in terms of surface water bodies changes in response to the atmospheric demand as indicated through the SPEI. So in conclusion, Prosper and our streamflow permanence models, through these modeling efforts, we have increased in spatial and temporal resolution of streamflow permanence classifications at regional scales and across various hydrographies. These incorporate unconventional and simple observational data. Essentially, it's either flowing or not flowing, and we can use that to train our models and come up with these predictions. And this is important because accurate classifications is a real need for land and water management decisions, and only will be more so moving forward. So we do have a streamflow permanence landing page in the USGS. Again, I know it's hard to capture this link, but again, feel free to reach out to me or Chris or Jason Dunham or Kyle Blosh. We'd be happy to point you towards these. We have all of our data provided here, all of our models provided here, as well as the publications associated with them, and data collection. Our Floper app can be found at this landing page as well. And that concludes my talk. So I guess, Tim, I'm happy to take any questions now if there are any.
Yeah, you bet. Thanks, Roy. What I think we'll do is we've got a couple in the chat, and I thought maybe we could do those first, and then we could turn over and see if any of the classrooms who are live in Boise or Pocatello have questions.
Sure.
So I don't know if you can see the chat, but I'll just jump to the first one here, which says, have you explored including soil moisture parameters in your model? If not, why? Do you think it could improve model performance? I recognize direct soil moisture measurements are spatially limited, but something like vapor pressure deficit, which could be more representative than ET and NDVI.
Yeah, that's a great question. We did include the GridMet soil moisture variable in our Upper Missouri modeling effort. I mean, it was marginally important. I think what happens is it's correlated with other variables so highly that it kind of drops out. But again, I think that your question probably gets back to the scale issue, right? For some basins, that soil moisture is going to be much more important than at the regional scale, and focusing in on those local instances is probably really important. Yeah, so it's a good observation. I think the degree of importance probably varies, but we did include that in our modeling effort.
Yeah, and then I just saw Chris chimed in the chat as well, saying VPD was considered in the Western Oregon model, and also dropped out in terms of final variables in the model. And then there was another request there that said, could you put the last link into the chat?
Yes, I will do that. Let me stop this presentation really quickly.
And so I think what we'll do is, actually, I just wanted to make sure that the live classrooms have an opportunity. I don't know if there's any here. Okay. Maybe just see if there's any in Pocatello first, and then we can jump to Boise and then back to the chat. So any questions from Pocatello if folks are live down there?
I think that there were a couple of questions were distributed today. So since I'm up in the Arctic, and I'll just ask folks to jump in if you've got any. Otherwise, maybe I'll jump in with one, Roy.
Sure.
One of the things that strikes me as a challenge with the accuracy of this mapping is knowing where springs are, because springs are so important for determining where streams are flowing more reliably. And I was just curious about your inventories of springs, accuracy of those inventories, whether that's been considered the sort of the groundwater surface water interaction component that's focused on springs.
Yeah, obviously a great observation. We've done our best to incorporate springs in the past. There's just no good data set to represent them. What we used in the past was essentially a spring presence absence data set, and found that wasn't terribly helpful because as I'm sure you know, what's important there is actually how much water is coming out of the spring, right? You can have a spring that's essentially dry that means nothing or very little flow, or you can have a spring that's like a gusher. And those are two completely different things, although they show up as the same thing in this data set that we used. So there was really no good inventory there. And moving forward, I mean, groundwater in general is extremely important, and currently is just one of the huge unknowns in all of this. So I don't know what the answer is there. I guess you know, better mapping, better observational data sets. I think this is a huge gap though in that streamflow permanence mapping arena for sure.
Thanks. Appreciate it.
Yeah.
I'm in Pocatello. I have a question.
Sure.
You mentioned that the model accuracy tends to hover around like 80%, so it's kind of like a ceiling that we're hitting. And I know that you mentioned some limitations on it. So I was curious, what do you think is like the biggest barrier to pushing that higher? Like, is it the data or the methods or like something else that can be used to get a higher percentage?
Yeah, good question. And so this is based on what, like 4 or 5 studies that we've done now, and they all of them seem to hover right around that 80 to 85% mark. I think one big thing that Sarah just alluded to is the presence of groundwater and its role in streamflow permanence. Another thing similarly is geology. We don't have great geologic maps that are high enough resolution to actually capture what's happening at the reach scale. So a couple of input variables there. Another huge question mark and thing that's difficult to quantify is the human footprint, right? So how much regulation, how much withdrawal. I know here in Montana, we're working on improving our water permitting database that might help. But again, even that's difficult because permits don't necessarily mean consumptive use. So yeah, I think those are 3 big ones though that would help reduce that uncertainty. Other than that, I'm sure that there's others, but those are the big ones that we've encountered in our work.
Thank you.
Yeah, good question.
All right. Is there anybody in the Boise room that has questions? I'm gonna pivot back to the chat. Again, I don't know if you can see those, Roy, but there's one there from Tao Huang, who's faculty down at Idaho State. Says, thanks for the nice talk. I love the idea about predictions based on model ensembles. Follow-up question, how would you effectively evaluate the different models' performance and combine multiple model predictions to help improve stream classification?
Yeah, so in model ensembling, I mean, each model would have, hopefully would have its own uncertainty and error associated with it. So we would obviously incorporate that as representative of each individual modeling error. In terms of combining those, I mean, I've seen, you know, ensembles represented as anything from ranges to confidence intervals to, you know, means or moments of a distribution. So I think partly it would depend on the end user and how they wanted to represent the output in terms of either conservative or liberal, you know, or a range of possibilities. I think from a scientist point of view, the goal here is just to provide as much information and transparency as possible, right? So yeah, publication of confidence intervals, predictions, prediction error, modeling error, all of those would be important to document for each independent model. So I feel like that was kind of a soft answer, and sorry for that, but I'd be happy to follow up if you want.
Looks like Kendra's got a question, so jump to Kendra, then back to the chat.
Hey, Roy, nice job summarizing a lot of work over a long period of time with a lot of people. The one thing I don't think I heard you touch on was that I know that you all have done a lot of engagement with various stakeholders on how to make these tools relevant for decisions that they're making. I'm wondering if you could just touch on your approach to engaging folks and maybe if there were 1 or 2 big things that you modified in response to their input.
Yeah, great question. So specifically, Chris and I worked on kind of a workshop with stakeholders over the past 3 years. And I know that you've got a lot of experience with this too, Kendra. So I'm sure, yeah, if you have something to add, please feel free. But one thing that we found out was the needs are vast, right? Like there's a huge variety in how people need this information. One of the biggest constraints on how usable these data are is accessibility. So being able to pull in, like the USGS has our data repository called ScienceBase, which is great. But just taking these data and like blasting them out on ScienceBase is not generally helpful. Which is why we've tried to do things like incorporate it in StreamStats, produce multiple user guides, make visualization platforms that are easy to use and easy to understand, and also visually appealing. It makes it easier for folks to pull that in and digest it. But again, it's really hard to touch, like hit everybody's needs on this. So yeah, I guess those are some things that we found through that workshop. Chris or Kendra, if you guys have anything else to add, please feel free.
That's great.
I'll-
Thanks, Roy.
I'll just chop in really quickly. There like what Roy said, this is Chris Yeager, what Roy said was accurate. And a big thing with like people who are trying to make a decision is they're needing a classification. So that threshold 0.5, below or above that, and turning that into a classification, people have really struggled with how do you turn this continuous variable into just like a binary answer. And it will depend on what their question is. So it is an ongoing issue, but what Roy was saying is, it's us trying to give them as much information as possible, and different in terms of also the uncertainty and also additional data sources so that folks can hopefully reconcile what to do with this information. And so there's a publication that's in review now that is kind of a workflow of how do you reconcile the different pieces of streamflow information that's available for a given location.
Yeah, thanks, Chris.
All right, I was going to jump to another question in the chat, which is, did data collection include correlation of water demand from surface water stakeholders? Year over year, this can be a great empirical source of water flow and seasonality.
Yeah, good question. No, it did not. I don't know. Maybe there's a national data set out there that represents that. I don't know of one, but if you have a link or a publication associated with that, I'd be very interested to learn more about it.
Then there's another one that relates back to the modeling question as well, which the question is, do you think these models could eventually replace conventional streamflow monitoring, or are they meant to complement it?
Yeah, good question. I certainly don't think the models can replace, well, who knows, man, with artificial intelligence, anything's possible, I guess. But my guess would be that these models are not meant to replace conventional streamflow monitoring. I think we have to get creative about how we monitor streamflow, particularly in headwaters, because taking a traditional continuous gauge up into a remote, high alpine basin is just it's not feasible. There's so many of them and it's so expensive to implement those gauges up in the headwaters. It's just not possible. So getting creative about what information we're collecting, where we're collecting it, those are the types of questions and efforts that we have to be investing in at this point, I think, to really expand the potential of these modeling efforts. I think that this is kind of the next frontier in streamflow modeling, is moving up into the headwaters, and understanding how connected headwaters are with downstream systems is really important.
And I'll just follow up. I've got kind of a granular question for you in terms of when you talk about what flow is and flow permanence, because I've been doing a lot of work in really small headwater streams. And a lot of these streams, they transition from this case, as you well know, where they're flowing, and then all of a sudden you get these discontinuous kind of pockets of flow, and then you have standing water, and then you have damp sand. So what would classify, do you actually have to see visible flow for the stream to sort of tick into that binary of it is flowing?
Oh, what a can of worms, man. I mean, even, yeah, when you're out collecting floper data, sometimes it's just like you can hear the stream, but you can't see the stream. So what does that mean, right? Like, is it subsurface or is it surface? There's a large gray area, I think, on almost every stream that it's very difficult to distinguish surface versus subsurface flow, flowing versus discontinuous. I don't know if we have a good answer. You know, in our Floper app, we've allowed people to select discontinuous flow, things like the size, sediment size, you know, channel width, all these additional parameters that hopefully will allow us to quantify some of those things. But I think that you've touched on, you know, again, like one of the next steps in all of this is characterizing not perennial, intermittent, or ephemeral streams, but these gray zones between those. Is a really important thing too. So yeah, very difficult.
Well, thanks.
Yeah.
Let's see, I think we are probably just about out of time. Yeah, we're about 3 minutes to the bottom of the hour.
Really quickly, I do see one more comment from William in the chat. Yeah, so funny enough, we just got a project funded in the Puget Sound. Chris is the PI on that, but we'll be looking at downscale climate projections. So we'll be incorporating some information on what is projected to happen under different scenarios in the future. So stay tuned for that.
All right, great, thanks. Folks, I want to say thanks to everybody. And thanks again, Roy, for a great talk. This is really interesting to see this work evolving.
Yeah, thanks so much. Really appreciate the opportunity.
All right, great. Hopefully we'll see y'all next week.
All right, sounds good. Thank you.
All right, cheers, bye-bye.